Hello everyone. This time, we're going to solve a linear programming model using Simplex method. For instance, given this LP model with two decision variables, where we let T, the number of tables produced, and C, the number of chairs produced. For LP model, its objective is to maximize profit equal to $70 times T plus $50 times C, subject to, we have two constraints. So the painting hours constraint, where 2T plus 1C is less than or equal to 100. And the second constraint, carpentry hours, right, 40 and 3C less than or equal to 240. T and C are greater than or equal to 0, the non-negativity constraint of the problem. The first thing we need to do is to convert the LP model into its equivalent standard form. In order to transform the LP model into its equivalent standard form, we need to convert each of the constraints into an equation by adding a slack variable. Slack variables are added to a less than or equal to constraints. For instance, for the first constraint, which is the painting hour constraint, it will become 2T plus 1C plus S1, the first slack variable, is equal to 100. The second slack variable is added to the second constraint, which is 40 plus 3C plus S2 is equal to 240. Once the constraints were converted to equations, we can now construct the standard form of the LP model. This is now the standard form of the LP model. In the objective function, we added the slack variables with zero coefficients, implying that they have no contribution to the overall profit of the problem. Profit is solely dependent on the number of tables and number of chairs produced. At the same time, S1 and S2 are also greater than or equal to 0. Slack variables represent the unused resources in each of the constraints. To show this, for instance, we are to produce 40 tables and 10 chairs. On the constraint 1, 2T plus 1C plus S1 is equal to 100. 2 times 40 plus 1 times 10 plus S1 is equal to 100. This is equal to 80 plus 10 plus S1 is equal to 100. Therefore, S1 is equal to 10. Which means, if you are going to produce 40 tables and 10 chairs, there would be 10 hours of painting time unused. In the same way, using the second constraint, 40 plus 3C plus S2 is equal to 240. If you are going to produce 40 tables and 10 chairs plus S2 is equal to 240, this is 160 plus 30 plus S2 equal to 240, then S2 is equal to 240 minus 190, or S2 is equal to 50. Same interpretation, if you're going to produce 40 tables and 10 chairs, there would be 50 hours of carpentry time unused. Once we're done formulating the standard form of the linear programming model, we can now start constructing the simplex tables or simplex tables. The simplex tables has the following headers. So we have the C sub j's, which represents the coefficients in the objective function. We have the basic variables column, the column for the decision variables. So for this case, we have T and C, and their corresponding coefficients are 70 and 50. And then we have the columns for the slack variables, particularly we have S1 and S2, and their corresponding coefficient in the objective functions are zeros. On each of these rows, we're going to enter the coefficients and constants of the variables on each of the constraints. For instance, in row 1, we're going to enter the coefficients of constraint 1 representing the painting constraint. So, constraint 1 is 2t plus 1c plus s1 plus slack variable 2 is not present on this constraint, therefore its coefficient is equal to 0, and the quantity or the right hand side is equal to 100. For the second constraint, that's 40 plus 3c, again 0 for s1 since it is not part of the second constraint, and then 1 for s2 equal to 240, the right hand side of the second constraint. S1 and S2 are the basic variables for tableau 1 because actually we are letting T and C, the value of T and C equal to 0. Therefore, the value of the slack variable is 100 and S2 is equal to 240. These are the unused hours for the painting and carpentry time, since at this time the number of tables is equal to 0 and the number of chairs is also equal to 0. The next part of the simplex tables is the row for z sub j. We can compute for the entries of z sub j using this formula. Z sub j is equal to summation of C sub j times R sub j. C sub j's are the coefficients of the basic variables in the objective function, and R sub j's are elements of each corresponding row. So for instance, if where C sub j is 0, the coefficient of S1 times the elements of row 1. Plus, the second C sub j is also 0, and the elements of row 2 get the product for each element, and then you take the sum. Since the coefficients are equal to 0, the products are all 0, therefore all of the sums are equal to 0. And the entries for z sub j's are all zeros. The last row we're going to enter is the row for c sub j minus z sub j. The coefficients in the objective function minus the elements of z sub j. These are the elements of c sub j's. Again, they are coefficients of the variables in the objective function. So if you take the difference, 70 minus 0 is 70, 50 minus 0 is 50, 0 minus 0 is 0, and the last 0 minus 0 is again 0. So this will be our first Simplex tableau. So it simply means that the number of tables at this point is equal to 0 and the number of chairs is also equal to 0, and the unused hours for constraint 1 is 100 and unused hours for constraint 2 is 240. At the same time, P is also equal to 0, which is this value. Simplex method is an iterative process, so meaning the process will continue until such time it satisfies a particular condition. So for this case, the condition we need to satisfy is the elements of C sub j minus Z sub j should be less than or equal to 0, or the elements should be zeros or negative. And for this case, that condition has not yet been satisfied, so because we have two positive numbers on this row. To proceed to the next iteration, first we need to identify the most positive value in this row, C sub j minus Z sub j. The most positive value is 70. Therefore, we're going to call this column as the pivot column. And then we're going to take the ratio of the quantity of the column of the quantity to its corresponding element in the pivot column. So for the first ratio, that's 100 over 2 equal to 50. The second ratio is 240 over 4 is equal to 60. In these two ratios, we're going to choose the least positive number. The least positive number in this case is 50. This implies that row 1 will be our pivot row. At the same time, in the pivot column, the decision variable t will be what we call the entering variable. And the variable in the pivot row, which is S1, we will call this the leaving variable. On the next tableau, S1 will be replaced by the variable t. S1 will exit or will leave, and variable t will enter as a basic variable. The intersection of the pivot column and the pivot row, we will call it the pivot element. And the elements of the pivot column, such as 2 and 4, we will call them intersection elements. So now, we're ready to compute for the entries for the second tableau. We're going to compute for what we call the replacing row, or simply RR. This is equal to the pivot row divided by the pivot element. So for this case, the pivot row elements are 2, 1, 1, 0, 100. Divided by the pivot element is 2. Therefore, the elements of row 1 or the replacing row is 1, 1 half, 1 half, 0, and 50. The other rows, the entries for the new rows, so for instance, new R2, which pertains to this row, is equal to the elements of the old row 2 minus the intersection elements times the replacing row. This is equal to the old row 2 has elements 4, 3, 0, 1, 240 minus the intersection element for row 2 is 4 times the replacing row 1, 1 half, 1 half, 0, 50. The result of this, 4 minus 4, which is 0, 3 times negative 4 times 1 half, this is negative 2 plus 3, that's 1, 0, minus 4 times 1 half, so this is negative 2 plus 0, that's negative 2, and 1 minus 0, that's 1, 240 minus 200, that's equal to 40. So this is equal to the entries of row 2. So once the replacing row and the new elements for the new rows are computed or determined, we can now start constructing the second tableau. The basic variable for row 1 now is t, since it has replaced the variable s1. And then the second basic variable is s2. The coefficient of t on the objective function is 70. Coefficient of s2 in the objective function is 0. And the elements of row 1, which is the replacing row, that's 1, 1 half, 1 half, 0, 50. The second row, or the new R2, the elements are 0, 1, negative 2, 1, and 40. We can now compute for the values of z sub j. Again, z sub j is equal to summation of c sub j's r sub j equal to, so the first variable is t and its coefficient is 70 times the elements of row 1, 1, 1 half, 1 half, 0, 50. Plus the second basic variable is s2, its coefficient is 0, 0, and the elements of row 2 is 0, 1, negative 2, 1, 40. The result of this is 70 times 1 plus 0, that's 70. 70 times 1 half plus 0, that's 35. 70 times 1 half plus 0, again 35. 70 times 0, that's 0 plus 0 equal to 0. And 70 times 50, that's 3,500 plus 0 is 3,500. So these are the elements of z sub j. 70, 35, 35, 0, 350. Next would be the elements of c sub j minus z sub j. 70 minus 70, that's 0. 50 minus 35, that's 15. 0 minus 35, that's negative 35. 0 minus 0 is equal to 0. So this will be our second tableau. Second tableau means that t is equal to 50. C is equal to 0. S1 is equal to 0. And S2 is equal to 40. This means that if we're going to produce 50 tables and 0 chairs, all of the painting hours will be used up, and in the carpentry time there would be 40 unused hours. And at the same time, in producing 50 tables and 0 chairs, the profit would be 3,500. In this iteration, we're now going to check if this is already the final tableau or what we call the optimal solution. Again, we need to check if the elements of c sub j minus z sub j are all zeros or negative. So as you can see, we still have one positive value. Therefore, tableau 2 has not yet provided the optimal solution of the problem. So again, we need to identify the most positive number in this row, which is 15. Therefore, this is the pivot column, and taking the ratios, 50 over 1/2, this is equal to 100, and 40 divided by 1 is equal to 40. So the least positive ratio is 40. Therefore, this is the pivot row. C will be the entering variable and S2 will be the leaving variable. Now we can compute for the values of the replacing row. Replacing row is equal to the pivot row, which has elements 0, 1, -2, 1, 40, divided by the pivot element 1. Since it is divided by 1, the replacing row is equal to itself. Then, the new R1 is equal to the old R1 with elements 1, 1/2, 1/2, 0, 50, minus the intersection element of row 1 is 1/2 times the replacing row 0, 1, -2, 1, 40. The result would be 1 minus 0 is 1, 1/2 minus 1/2 is 0, 1/2, this would become positive 1, so that's 3 over 2. This is 0 minus -1/2, that's -1/2. 50 minus 1/2 times 40, so -20. 50 minus 20, that's equal to 30. The elements of row 1. We are now ready to construct the third tableau. So for row 1, the basic variable is t. For row 2, the basic variable would be c, which is the entering variable. It replaced the variable s2. The coefficient of t in the objective function is 70, and for c is 50. The elements of row 1, 1, 0, 3 over 2, negative 1 half, 30. Elements of row 2, which is the replacing row, 0, 1, negative 2, 1, 40. So for the elements of z sub j, 70 times the elements of row 1, 1, 0, 3 over 2, negative 1 half, 30, plus 50 times the elements of row 2, 0, 1, negative 2, 1, 40. So this is 70 plus 0, that's 70, 0 plus 50, that's 50. This is 70 times 3 over 2, so that's 210 divided by 2, that's 105, plus negative 100 equal to 5. And then this is 70 times negative 1 half, that's negative 35, plus 50, that's positive 15. Next, 70 times 30, that's 2,100, plus 50 times 40, that's 2,000. So 2,100 plus 2,000, that's 4,100. So the elements for z sub j row are 70, 50, 5, 15, and 4,100. Now the elements for c sub j minus z sub j. So 70 minus 70, that's 0. 50 minus 50, again that's equal to 0. 0 minus 5, that's negative 5. 0 minus 15, that's negative 15. So this is the third tableau. So what does this tableau implies? The solution that it provides is t equals 30, c is equal to 40, s1 is equal to 0, s2 is equal to 0, and the profit is equal to 4,100. The solution implies that if you're going to produce 30 tables and 40 chairs, the profit would be 4,100, and all of the painting and carpentry time are used up since the value of the slack variables are equal to 0. In the next step, we're going to determine if this table or this tableau is optimal. Again, the optimality condition we need to satisfy is c sub j minus z sub j should be greater than or equal to 0, or all of the elements of this row should be zeros and negatives. So as you can see, none of the elements are positive. Therefore, the condition is satisfied and tableau 3 is already the optimal or the final tableau of the problem. And t equals 30, c equals 40, and the profit equal to 4,100 is the optimal solution of this LP model. Another information that we can extract out of the optimal tableau of the simplex method is the economic value of each of the resources available. And the profit contribution per unit of painting time is $5 and the profit contribution per unit of carpentry time is $15. Since all of the painting time and carpentry time were used up, therefore $5 per unit of carpentry time times the number of hours used plus $15 times the available carpentry time is 240. This is equal to 500 plus 15 times 240, that is 3,600, which is equal to 4,100, which is actually the total profit in producing 30 tables and 40 chairs.